Hello, my name is Aryyama Jana, and here is my co-author Rudrendu Kumar Paul. And we both have designed this wide architecture deep learning model named xCovNet, which accurately identifies COVID-19 cases using chest X-ray images. Here is a brief overview of the structure of our presentation today. We'll be starting with the motivation and key goals for our research work and ending finally with comparing the performance of our model with respect to some models which we have taken as benchmark. Coming to the motivation, we all know that COVID-19 has been one of the major challenges that the world has been facing since its inception in 2019. And this has posed serious challenges not only on the developing countries, but also on the developed countries in the world. We know that there have been a lot of efforts to find a cure for this disease, but unfortunately, we don't have a cure yet. And most of the administrative authorities in various countries throughout the world still depend on the COVID-19 testing techniques to mitigate this challenge. One of the serious issues that comes to my mind is during air travel. We know that each and every government throughout the globe has put some COVID-19 testing protocols, and they are very strict on that for both international as well as domestic air travel. RT-PCR is the known gold standard for all these kinds of tests. But again, the downside for that is you need to wait for a lot of time to get the results. And just think about a case that, let's say, a person who is traveling internationally gets tested, let's say, a few hours before his travel. And what if he gets infected just before his departure? We miss out on those cases. And especially since we have a lot of common long distance international travels, which are usually 16 to 17 hours long, this risk is pretty serious because even if there is one false negative case, I feel that there is a huge chance that a lot of passengers who are surrounding that particular passenger will get infected and they have to get isolated and get all the medical attention. Another solution that has been there since the last few years is the rapid antigen test, which gives the results in 15 minutes. But the accuracy of these tests have been scientifically proven to be very low. And there is a high amount of false negatives and false positives for these tests. One of the proposed solutions I see in many of the research papers is using CT scans, because the CT scans are very highly accurate, but for practical purposes, it makes it very difficult and expensive to set up a CT scan machine in a COVID-19 testing kiosk at any of the airports throughout the world. So we think that a potential solution for this can be to develop a deep learning based model that can use the existing fast chest X-ray medical technology to classify a patient into COVID-19 or a non-COVID-19 patient. The key goals for our research include that we leverage the existing pre-trained models so that we get higher precision, sensitivity, and accuracy, although we have a low training data. And also we want to concatenate the different model features so that we can perform better than the already existing models in the market. This is a brief block diagram of the model that we are proposing over here. As we see that we are using 3 state-of-the-art models, and these are pre-trained models on the ImageNet dataset, as can be seen from the figure. So the models are DenseNet, ResNet, and MobileNet. We are using transfer learning over here, so we are retraining the last few layers of these models and then concatenating the features to finally classify the X-ray image into one of the 3 classes, that is normal, COVID-19, or pneumonia. Now let's see the detailed model architecture. So if we see the detailed model architecture, we see that it is a supervised learning method, and the image goes through each of the 3 pre-trained models, that is ResNet, MobileNet, and exception. Finally, we concatenate the features of these models that we get from these models, and then we finally pass it through the dense layer to get the final outcome that the passenger is either suffering from COVID or pneumonia or normal. So this can be for passenger or as well as for any patient in a hospital. An interesting thing to note here is that we are using a global approach as opposed to the patch-based approach that are recommended in various papers. This is because we wanted to ensure that we don't miss out on any of the features, and we have enough confidence in proposing our model for all the real-world applications.
Yes, I'll be talking about the datasets here. So at a very high level, we have 2 different datasets, one for developing the models, and the other one is an external validation dataset that was created using a different dataset, not that didn't have any overlap with the existing training dataset used for training the models. And so the datasets, we have 3 different classes: COVID-19, normal, and pneumonia. So for the training, validation, and testing sets, we essentially combine 2 different sources, one from the University of Montreal and the other from the Kaggle dataset. And we created a balanced dataset consisting of like 192 normal images for training, 41 images for validation set, and test had 41 images for each of those classes. So essentially, we split the dataset into 70-30, 70%, 15%, and 15% for each of those batches. And finally, for the external validation dataset, we had a total of 525 images, and we used the IEEE data port and the Mendeley's dataset to create that dataset. So here we are showing the performance of the individual backbone pre-trained models that we used. We have DenseNet, MobileNet, Exception, and ResNet, and we trained the models on our training dataset and then evaluated their performance on the validation set. And the validation losses are shown here. And the overall accuracy is pretty good here. But what we'll show you in the next slide is once we combine these models, we can actually achieve even higher, better performance than the individual models. So here we have concatenated the features from the individual backbone models. So DM, for instance, here refers to combining the DenseNet and the MobileNet models. And then the RMX here refers to the ResNet, MobileNet, and exception models. And as we can see that the overall accuracy, precision, sensitivity, and F1 scores are kind of similar across the different models. But for RMX, we can see that we selected the RMX model solely on the basis of validation loss. We can see that the validation loss is kind of the least for that model across all other models that we run experiments on. And this is the model we finally selected to test on the holdout or the holdout dataset, and also the external validation dataset, and where we achieve significantly higher accuracy. And here we have used for benchmarking purposes the external validation dataset. So O et al.'s model has used this dataset for developing their model, and they published their accuracy, F1 scores, and precision and recall scores. So we have tested our model on this particular dataset and then did a binary classification. And as we can see here, the F1 score and precision scores are much higher than the O et al.'s model, but the sensitivity is slightly lower. So this gives us very high confidence that this model, although was trained on a completely different dataset, is doing really well on an external dataset where it was not trained on in the past. And finally, wrapping up, we saw that xCovNet is a very fast and economic way of detecting COVID-19 cases, and this will essentially can reduce the workload at the different healthcare testing facilities during peak travel times. And also, this uses X-ray images, like digital X-ray images, which are very cheap and can be performed very efficiently at different centers. The second thing we saw is the reduced size of the dataset. So because we are using a pre-trained model architecture, we required very small size of the dataset, and also we didn't have to train the models from scratch. That saves significant time for training time as well. And so because we achieved very high precision and sensitivity on the external validation set, we can say that this gives us a lot of confidence that we can potentially deploy these models in case of mass screening for large population centers. Thank you.